Magali is studying the mean total cloud cover in octas for Lucas in 1987 using data from the large dataset. The daily mean total cloud cover for all 184 days from the large dataset is summarised in the below table. One of the 184 days is selected at random, and part A says we need to find the probability that it has a daily mean total cloud cover of greater than 6. Okay, so looking up here at the table that summarises the data, if it has a cloud cover of 6 or greater, we see, okay, so it has to be 6, 7 or 8. And adding up the corresponding values here, we're going to have 52 plus 52 plus 28. So that's 132. So that's 132 days out of the total of 184 days. So if we do that, we're going to have 132 over 184. And that simplifies down to 33 divided by 46, which is our final probability. And we get the 1 mark here for getting the correct final probability, either like this as a fraction or as a decimal or percentage. So next it says that Magali is investigating whether the daily mean total cloud cover can be modelled using a binomial distribution. She uses the random variable x to denote the daily mean total cloud cover and believes that x can be modelled by this binomial distribution here. Using Magali's model, we need to firstly, in part B, find the probability that x is greater than or equal to 6. So look at this, the issue that we've got is in our calculators, they're set up to work out probabilities using the binomial distribution in this format here where we've got our random variable is less than or equal to something, rather than here where we've got our random variable is greater than or equal to something. So if we can write this in this form, then we can put it into our calculator and work out the final answer. So I'm going to write out some numbers to help demonstrate this. And we're finding the probability of x is greater than or equal to 6. So I'm going to start with 6. And I'm going to write some numbers greater than it. So we've got 6, 7, 8. And I'm going to go the other way as well. Go 5, 4. And drawing on at the minute, what we want to find is the probability that x is greater than or equal to 6. So here. Now the trick to use is that you then take this and imagine flipping it over. So if I do that, I get this region here. So flipping over our final region that we want, we get this region, which is that x is less than or equal to 5. And we need to remember that when we flip it over like this, what we need to do is 1 minus the new probability. So essentially, the probability of x is greater than or equal to 6 equals 1 minus the probability of our new region here. So x is less than or equal to 5. So going into the binomial CD menu in our calculator, we can input our upper value as 5. And look up at the distribution used. We see we're going to input n to be 8 and p, so the probability to be 0.76. So doing that, we're going to get 1 minus, then the value that the calculator gives us, 0.296722 ... And if we evaluate this, that gives us 0.703 to 3 decimal places. So looking through, we get 1 mark here for realising that we can write the probability that x is greater than or equal to 6 as 1 minus the probability that x is less than or equal to 5. And then we get the second and final mark for working out that the final probability is 0.703. So now the second part B says we need to find to 1 decimal place the expected number of days in a sample of 184 days with a daily mean total cloud cover of 7. And this for 2 marks. Okay, so again, we're going to be using the same model that we used in the previous part. However, looking here, we see that the random variable x denotes the daily mean total cloud cover. However, we don't want it just for 1 day, we want it for 184 days. So to work out the expected number, what we're going to do, we're going to work out the probability that x equals 7. But then, because we don't just want 1 day, we want 184 days, we're going to just multiply it by 184. So we can evaluate this in our calculator, this time using the binomial PD menu, setting x equal to 7, then using the same values for n and p as before, so 8 and 0.76. And doing that, we're going to get out from the calculator 0.2811 ... And we're going to multiply that by 184, which equals 51.7385 ... which equals 51.7 to 1 decimal place. So you get 1 mark here for realising that we need to multiply by 185. And we get a second mark here for the final answer of 51.7. So in part C, we need to explain whether or not our answers to part B support the use of Magali's model. So we can look at a couple of different things. First, if we compare part A and part BI, we see in part A the probability of a daily mean total cloud cover of 6 or greater is 33 over 46, which is 0.717. And look at what we got in B part 1 when we use the model. We got 0.703. So the numbers are relatively close, so that shows that the model is likely to be quite accurate. Then we can also compare something else. So look at B part 2. We see that for over 184 days, we see the expected number of days in a sample of 184 days with a daily mean total cloud cover of 7. The model says that it should be 51.7. And if we look at the actual data from the large data set, we can see it was 52. So those are really similar. So that shows again that the model is likely to be accurate. So we say that part A and part BI are similar. And also the expected number of 7s matches the number of 7s in the data set. So Megali's model is supported. And we get 1 mark for writing a statement along the lines of this. So there were 28 days that had a daily mean total cloud cover of 8. For these 28 days, the daily mean total cloud cover for the following date is shown in the table. And part D says we need to find the proportion of these days when the daily mean total cloud cover was 6 or greater. So similar to in part A, when it's 6 or greater, it's going to be this. So 6, 7 or 8. So if we add up the corresponding numbers, we're going to get 5 plus 9 plus 9, which equals 23. And that's out of the 28 days that the table represents. So we're going to have 23 out of 28. And that equals 0.82142, ... which equals 0.821, 3 decimal places. I'm going to get 1 mark here for getting the correct proportion. So lastly now, part E says we need to comment on Megali's model in light of our answer to part D. So look at this in part D, from this set of data here. When the daily mean total cloud cover was 6 or greater, we got the proportion to be 0.821. However, this differs from what we got from this data in part A, because if we remember 33 over 46 equals 0.717, and it also differs from here in part B, part 1, which is 0.703. So these two are quite similar. However, with this one, the difference is greater. And because in this table here, the data is for a day that follows, where the previous day had a high cloud cover, so a cloud cover of 8. It seems like there's more likely to be high cloud cover if the previous day had high cloud cover. So this sort of suggests that the days aren't independent. So the cloud cover on the previous day could affect the cloud cover on the next day. And we know for the binomial distribution, the trials, so in this case the different days need to be independent. So this would suggest that Megali's binomial model might not be suitable. So we say that part D differs from part A and part B. So look at that, the conclusion that I would then come to. Therefore, Megali's model may not be suitable. So you get 1 mark here for the first line, so for having some sort of justification and giving some evidence. And then we get a 2nd mark for coming to the conclusion from that evidence.